Okay, so what's up? The name is Ange Manuel. Today I will be recording a video to attempt to explain in a way that makes somewhat sense. I mean, it makes sense to me, but like, hopefully that will make sense, at least to some extent, to you too. And so that you'll be able to reproduce it if ever needed. Of why the doubling method versus the constant increment method have respectively an big O of n and n squared. And yeah, that's basically it. That's gonna be what we're gonna be trying to do today. I do not have a script right now, so if you see me looking for my words, looking for analogies, correcting myself, mumbling, all of that, I'm really recording this as if I was like talking to myself and working through it. So hopefully it will make sense. Likely some parts will not. So I feel like it's probably really important to first start by explaining what is time complexity in the first place. Time complexity, the best way you can think of it is literally just the amount of steps it takes to do stuff. Okay? Let's say right now I'm at home, right? And I want to know how long it takes to go from my bedroom to the kitchen, as opposed to going outside, as opposed to going to my brother's room, etc., etc. Okay? I could literally just time myself. Or in a program, I could literally just log the starting time, log the final time, and then do it that way. Okay? But I could, if I know roughly my span and everything, and I know how fast I walk, I could have an idea that makes sense to me of how quickly I can go to every place by literally just counting how many steps it takes to get there. If you want a better analogy in that context, it'd be like more like measuring measuring the distance, dividing by my step span and everything, so that you have a real theoretical step thing. But like, that's the gist of it. So if I tell you that it takes me 20 steps to go to my brother's room from my room, but 50 steps to go outside, it would mean that unless I have a real big fear of grass, that it takes less time to go to my brother's room than to go outside. So now what about orders? Orders, really the easiest way to think of them, like that's at least how I think of them. I don't know if there's probably something simpler, maybe. Just think of them as units, okay? Whenever I'm talking about big things, let's say a tower, like the Eiffel Tower, if I really want it to be an annoying, well, really, I don't need to insult anyone. If I really wanted to like do it precisely, let's say, I could go down to the micrometer, right? But like, when you really think about it, I could add 4,000 micrometers. It won't change much at all, like to the actual height of the thing. If I tell you that this tower is 2,000 meters tall, 4,000 micrometers plus or minus that is still gonna be roughly 1,000 meters tall. If I tell you that United States are like, that's a random number, I don't know, and I won't look it up, 10,000 kilometers from Japan, you could add 1,000, like even 100,000 centimeters to that. Okay, yeah, it might have some impact at that point, but like, at that you can add like a lot of centimeters to that, and it won't matter that the thing that really matters here are the kilometers, right? Kilometers, orders, kilometer, like the unit that you're using essentially tells you what's the thing that's most important in that context. I think a better way to think of it is that, okay, if let's say I have n plus 2 here. Here, this is the units of n. but that n here can change, right? Let's say that's a unit of meters and that's centimeters. Okay, that centimeter here is staying constant. This one, since it's associated to n, will actually be able to change. Wow. Wow. That's not a good analogy. Okay, let's just ignore that. Let's just scratch that. We're just gonna stick. I'll think later about an analogy that makes sense. But units is really how I conceptualize orders, right? And so for that reason, if I have n2, everything else doesn't matter because this one will just grow much faster. I could have n squared plus 1,000 n. Maybe for the first few bits, this will be much smaller than this, right? But as n grows to infinity, this will become much bigger than this. Okay, essentially, the moment where n is at least as big as this is destroying that. And like literally, how many zeros do I have? 0, 0. Yeah, like that times boom. Yeah, that's bigger, and then after that, it's just like landslide. But that's not what you care about. Right now, we really took 6 minutes just to explain time complexity. Okay. What we want to talk about now is algorithm and time complexity. What I was trying to get at is essentially, when we're talking time complexity of an algorithm, we're essentially just counting the amount of steps it takes to complete the entire thing. And we often take shortcuts when like we're talking about like for this, that, blah, blah, blah. Because the same way, like when I'm talking about like big units of, I know like n is that much bigger than like any given constant, right? When we know that this n is there, like when I know that like something is measured in kilometers, I probably don't care much about the centimeters anymore. Okay, so we take shortcuts like that, but really, if you want it to be precise, you need to like keep track of everything, which is what we'll be doing for the proof here. So let's say we'll start with doubling, and we're talking about extendable arrays. So since we're talking about like steps, and like really you're going to be hearing me saying steps a lot, but the idea is that you want to be able to count how many steps there will be for each and every thing, essentially. So I have phase 0. What is phase 0? In math, I'm just trying to like I'm just naming this here because it makes more sense later. But like just in math in general, you start with 0, right? So that will be my initial phase. And since we're doubling, what is the smallest thing I can get to that will still make sense as an array? 0 wouldn't make sense. A decimal number wouldn't make sense. Like I couldn't have an array with like 0.5 places. So the smallest I can get to is gonna be an integer, and it's gonna be 1. Okay, so I have an array of size 1. Now I need to think about that problem. Okay, when I'm doubling, what is gonna be the thing that's gonna be taking me time? Is just essentially the act of like adding stuff in and doubling each time I need to do that, right? And so when I think about it, there are two possible cases whenever I'm adding something to the array. Either the array is empty, in which case it's O of 1, and I do one step to go from here to that. Or if it's not empty, then it becomes this thing here. I need to create a new array, but I'm gonna be creating like each block, each location for that new array will be one step. Like think of it as like stacking Legos, right? You take one Lego from the box. That's one step already right there. You take another Lego and put it there. Technically, you could break it down to like 2 steps, but like we're just gonna be counting it as like stacking the thing as one thing. Okay, so you take another one and put it there. That's another step. Boom, boom, boom. to n, essentially. So now, right there, just from the simple fact of like stacking these two together, I got 2 steps. Okay. Then I need to copy whatever was here to my new array. And only once that's done, and so that's 1 step still, but you'll see that this part here will be growing as we increase. I will be adding 1 element. This is the only constant part in the entire process, because the idea is always to like we need to do all that just for that single element, which is what we're trying to add in the first place. So that's the explanation behind it, but really we see that we have 2 cases, the regular case and a special case. At phase 0, each happens exactly once, but this one is the regular case because at any size greater than that, this will be what will be happening most often, and this one here will in fact happen exactly once. But as you can see by the demonstration here, each time I have at least 1 empty space, I have only 1 step to do to add my object in. But when I need to do a special push, I'll need to do all of this, this entire like process, just to add that 1 element in. So even though there will be more overall, let's say, operations here than here, if that makes sense. Like we're gonna be like going through more things there. I'm gonna be doing more steps here. I don't know if what I just said made sense, but yes. So we see that at phase 0, since I'm filling it once, I'm gonna have 1 step there, and you're gonna like you can convince yourself pretty easily. We're gonna do the first 2 phases or something. That number here will always be just the length of the array, right? Because I can always fill it without having to worry about a special case. At least exactly the length of the array. Okay. And then when I get to the special case, which is when the array is full, I will first need to double whatever I add first, which is boom. And it would probably be better to like write this in a different color so that we can see easily where it is. Okay, boom. Okay. So I need to double whatever I add here. Okay. Oh my gosh, the tablet is dysfunctioning. Okay. Then I'll need to copy whatever I had here to the new array. When we're copying, we're basically just doing regular pushes to that new array. So, boom. We're gonna always have the exact same amount here. And then finally, what we're trying to do in the first place, we're gonna be pushing that 1 element that we're trying to add. Okay? That's really the logic. Why are we doing all that? Really simply for the sake of like helping ourselves find stuff, because we're trying to like find what it looks like when I or n gets really big. But unless you're a super genius or a computer or like God, I don't know, you need stuff to infer that judgment based on. Okay, that was a weird sentence, but okay. And so all of this here, once we found the pattern, it might take us 0, like we might be able to like find it instantly because like we already know what we're doing. In this case, we're walking through it, so like we're gonna need more than that. Or we might have to go to the 10th phase maybe to like find the pattern we're looking for. Hopefully not, but like it could happen. The idea is just do as many phases as you need to find what the pattern is. So right now there's nothing really obvious except the fact that this one here is going to be repeating here, and we're going to see at phase 1 and 2, then just that this element here just repeats there each time. So so now we're at phase 1. Now that we doubled the array, we now have an array of size 2. I won't be redrawing the thing each time, but like just for visualization, that's there. We can see that we're gonna have 2 regular pushes here, same as the length of the array. And then when I do the new thing again, when I do the special push, oh, I'm not consistent with my colors. That's what happens when you try to record without planning. You're gonna have 2 here, which is the 2 from just doubling the array. Another 2, which is the 2 this time from the length of the array. Plus the 2 again, which is the 2 of the length of the array again. We're just copying every element in that first array in the new one. And then 1, which is the thing from what we needed to do. You might be able to stop here, depending on who you are, but we'll do the last step because that's when it gets really clear. Okay, so phase 2, we got reg, and we got spec again. Colors are annoying. Okay, so see how when we're here we double from 1 to 2. Now when we're at the second phase, we're gonna have an array of size 4. Each time we're simply doubling. And so, yet again, I'm gonna be able to push exactly 4 times without having to worry about anything. Exactly the length of the array, 4. And then I will have 2 times 4 again, repeating term, plus 4 plus 1. At this point, I hope what like each of these, what the 2 here means versus that 2 versus the 1 here, what it all means, I hope that this makes sense to you. Now, we're stopping here because at this point you should be able to see what kind of pattern we're going through. If you're not, really don't worry, it's really just a matter of like pattern recognition. Once you've seen this, problems that follow a similar pattern will like just jump to you. But yeah, the idea is that we're in computer science. If you're watching this, you're in computer science probably. So you already should be used to like power of 2s, to power of 2. So this is just 2 to the 0, and this is just 2 to the 1, and this is just 2 to the 2. The interesting thing is that we see a relation between that 2 here and that phase number we're at. Is that a coincidence? No. I mean, like if you had started with 1, it wouldn't have given you something that pretty, but like we see that relation there. So based on that and the fact like you could replace all of those with what I just wrote here, you're going to be able to see that like at any arbitrary phase I, you're going to be able to do exactly 2 to the I regular pushes, which will be the size of the array at that point. And you will need to do that amount of operation for the special push. Well, that it's going to be an equation that follows that form. That's what I meant. Which will be 2 times 2 to the I plus 2 to the I plus 1. Really, it's just a matter of like seeing the pattern we have here and then trying to generalize it. Now, and that's where the steps from earlier comes from. Remember, the idea is like just to find how many steps in total it takes to do everything. There's one operation that's happening here, but that operation takes that many steps. There's that many operations happening here, but it just so happens that each operation takes exactly 1 step. So yeah, that's how it works out. But since right now we have like the step number that it takes, we want to know for any given phase, and like we're going to be working with the abstraction from now on. For any given phase, what is the sum, like what is the amount of oh my gosh, what is the amount of steps that will be required to complete it? Okay. What the heck? Okay. Abort mission. Okay. Good. So this is an amount of step. This is a given number of steps. This is not a given number of steps. I want to know the total for that phase, so I just sum them up. So I have 2 times 2 to the I plus 2 to the I plus 1 plus 2 to the I. I think you can all agree with me that this is equal to 2 to the I, that it is the same thing as 2 to the I plus 2 to the I here plus 1. Like I literally just brought that here. And now you will need to flex those law of exponents of muscles of yours. Wow, that was a weird sentence. Anyways, to flex those to simplify this even further, because you could go from there if you wanted to, but it's going to be a pain to work with. So, okay, I have 2, same basis. That's the same as 2 to the 1. So I'm just going to write this as, based on like my, I won't write them, but like based on my exponent rules, if I have the same base, I can just add the exponents. So this is 2 to I, to 1 plus I, right? Here I have 2 plus 2I plus 1. This here, I think you can agree that it's the same thing as just saying 2 times 2 to the I. And based on the same exact argument that we just had here, that here is equal to 2 to the I plus 1. 2 to the I plus 1. Or 2 to the 1 plus I, it doesn't change anything. And there's nothing we can do with that one. I mean, you could, yeah, there's nothing we can do with that one. So we're just gonna leave it at that. Then, same logic as above. That 2 to the I plus 1, 2 to the I plus 1, that's the same thing as saying 2 times that, 2 to the I plus 1, plus 1. And so you get, in total, in the end, 2 to the I plus 2 plus 1. If this didn't make sense, just review your laws of exponents. It's really, that's the only thing we're using there. And so we know that for any given phase, we're going to be doing exactly 2 to the I plus 2 steps. And so let's test that formula to see if it works with what we know, with what we have. Okay, so let's go to phase 0, for example, where I is 0. When I is 0, we get 2 to the 2 plus, so 4 plus 1. We have one step here. We have, so we're expecting to get 5, right? We have one step here, plus 1, that's 3, plus, boom, 5. So 3 plus 2, 5. If we could test it further, but like, yeah, that, I'll let you do that on your own. That's the simplified form of what we are getting at. And now that we got a general form for the entire, for a given phase, how do I generalize, how do I know the entire thing for all of those though? Like now I know for that group here, I don't need to worry about it anymore. How do I find it for those? That's when you use a summation. That's when you use a summation, which is going to be this here. From what we have above, we can start our summation at 0. The inside of the summation is just going to be that formula here. 2i plus 2 plus 1. Now, if you know how summations work, you know that we need something to put here. The thing is, at this point, we don't have anything to put. So what do? That's when the thing can get tricky. You need to like find what's the relationship between I and your n, because you could assume that this I is just going to go to n at some point. No, it's not. It's not. when we're talking about n, we're talking about the size of the input, the size of like the array we're working with. So you need to assume that at some point, what will reach n will be the length of that array itself. Okay. Thankfully, if you okay. Thankfully, we know that we're always gonna be doing the as a number of pushes to the array, 2 to the power of the current phase, right? And that number of pushes to the array is also exactly equal to the length of that array. Which means that when we get to a point where like that number of regular pushes is just n, we're gonna have n be a power of sum of 2. So like it's gonna be 2 to the power of x, let's say, is equal to n. The thing is, we see from the relation between this and that, okay, the power here is always just the phase there. And so if I know the phase already, and I know the base of it, the thing that allows me to find what the power of that is, okay, I know what the result is. I know what the result is. I don't know what x is, but I know what the power is, but I know what the base is. It's going to be logarithm. Like if I have 2 to the 3 is equal to 8. Okay. And I wanted to like get 3 somehow. Without knowing that, I need to like go. It's okay. I always like to draw those like to better help myself. But essentially, the relationship is going to be that log 2 of this is going to get you 3. Because the log is there to help you find what exponent allows you to find the result you want for a given base. And so here, what we want to know is x, what phase number we need to reach for n to be the size of our array. Okay? And hopefully that made sense. This here, like that'd be the same thing. Like I could rewrite this as like 2 to the 8 is equal to 3. And so this here, by using that same logic like arrows, if I want to write the log, I'm just going to be writing this as log to the base 2 of n is equal to x. And x here, what is it again? That's the phase of the thing we're at, which means that that's the maximum x that's the maximum we're gonna be reaching, because when we get there we're at n, if that makes sense. And what were we lacking exactly? Yeah, the top of our summation, the maximum that I will be reaching, that thing here. So we just plug that to the top of our summation, and so now we got the summation of this 2 log 2n. Okay, so now there are 2 ways to go about it. Since we decided from the get-go that we try to like get the exact thing, we'll still try to be somewhat rigorous with it. But if you were really just trying to do it for like finding the order of something, the variable term is what's important in there. So like all the constant terms, you'd be able to just discard, because in the end they won't be the thing that matters when n gets really big, right? Only the terms that have variables in them will be important. We will ignore that convenient fact and go against that thing. It's not complicated at all. Remember your summation laws. If you don't remember those, just remember your integral laws. They're pretty much the same, they're pretty much the same. So I can split this in multiple integrals. I can take constants outside of the summation. Yeah. So I have this here. I have this one. I'm gonna be this one doesn't change. I'm just gonna be multiplying it. I'm just gonna be multiplying it by that. So I get that log 2 of n appears here. Okay. Then here I'm gonna be that log 2 of n is just gonna be following us around. I'm gonna be worrying about the inside now. Log 2n I is equal to 0. I see that like 2i plus 2. I combine it like this because it was more convenient when we're trying to simplify. But for the integral, it makes more sense to split it out. Why? Because I will get 2 to the 2 times 2 to the I. And that 2 to the 2, it's a constant, right? And it's a scalar, so I can just take it out of the summation and multiply it at the end. So I will have 2 to the I log, what was it, 2n, I think? Yeah, it was log 2n. I is equal to 0. And then 2 to the I plus log 2n. And that's where you really just need to be good at pattern recognition. Okay? This here is no longer so important because that's a constant. That 2 is already a constant. We don't care about this anymore. So let me rewrite this bigger. Summation of log 2n I is equal to 0 to I. Does it look like something familiar to you? Maybe if I write it that way, 1 plus 2 plus 4 plus, and then we're gonna reach, yeah. Maybe if I read it that way. If it doesn't make sense, if you just haven't made, like, it doesn't really need to make sense for that part of the thing, because the making sense part is really just math and proving that this is what, that this will be equal to like something else. But if you've seen it somewhere before, you know that this thing looks awfully similar to a geometric series, and in fact it is a geometric series. So we're going to be using the fact that the geometric series for, it's a geometric series with an a of 1 and an r of 2. A constant factor of, a common ratio of, well, ratio doesn't make sense, common factor of 2 in that case. Okay, so I will rewrite this entire thing here as that. And that's where CSI gets really confusing, and that's why I really don't like it, because, no, I like, the material is interesting, but like, you get a lot of variables which look like they mean the same thing, but they don't at all. In the formula for the geometric, if I remember it properly, you're gonna have, since r is greater than 1, you're gonna have a times rn minus 1 over r minus 1, if I'm not mistaken. The thing is, that n here, that has nothing to do with that hen there. So let me just change that to rm. Okay, and that's the other big difficulty when you're doing those. You just need to know what each variable stands for and like be able to like make that filter on your own. Okay, so I'm just gonna change that n to a m, and I'm pretty sure I didn't fuck up the formula. Yeah, that seems to make sense. Wait, let me look it up. Geometric. Yep, that's it. So m will be the amount of time I'm doing the summation. Okay, the amount of terms in my summation. In this case, I'm gonna have this here. So I'm gonna just be plugging the log to the m, into the m. Then the r is just 2, the a is 1, so we don't even need to worry about a. Is just, yeah. And this here, I'm not gonna be rewriting when I'm here because, well, it's 2 minus 1, that's 1, so dividing by 1 doesn't change anything. So the only part we really care about in this specific context is the top part. Okay, so this inner thing, when I use the compact formula, I think that's how it's called, for the geometric series, for the summation of a geometric series, I get 2i here times 2 to the log 2 n plus no minus 1 minus 1. So here, what do you do with that? I mean, if you know your log laws, that should be obvious. If it's not clear, what would you do if you had like e log nx? Like this simplifies to x, right? Because like those two just cancel out. In a similar fashion, log 2 that part here will just, like the base is 2, we have 2 as the base here. That part is just gonna simplify to 2 to the I n minus 1. Okay, and I still have plus log 2n outside. And so now it's really just a matter of like multiplying the terms together. 2I n minus oh wait. Why do I have 2i still? My bad, it's not 2i, it's 2. It's supposed to be a 2 here. Yeah, I was looking for, yeah, okay, that's supposed to be a 2. So 2 to 2 squared, so yeah, I'm just gonna write it as 4. There's no need to for that basis thing anymore. So I just get 4n minus 4 plus log 2n. And so now, as we were talking earlier about orders, you know that log n is a smaller order as n, the same way as a centimeter is a smaller order as a meter. So since the biggest order, the biggest degree term in there is n, everything else can just go wherever it wants, because our O of n, like our time complexity, will simply be O of n. If you want it to be exact, it'd be O of that thing here. But when we're talking like just in general, that's what we're going to be using. And so that's why everything else doesn't matter. So I hope that at least made a smidget of sense for that. Now, what about constant increment? I will be explaining a little bit less, because the strategy and the logic will be the same, pretty much. Like, we're just counting steps each time. We're doing a few phases just to see what pattern there is, and then we generalize that, and then find a way to take a form, like to take a summation, because each time we're trying to like find the total of the entire thing, right? So to take a summation of the entire thing, and usually that's going to simplify to some kind of conveniently proved summation that exists. So now phase 1, phase 0, my bad, array length 0. So it's going to take, we're going to have reg and special again. Instead that this time the special will, instead of doubling, will be plus a given constant. Okay, this time relationship will be a bit more straightforward, even though it doesn't feel like it. Well, after working from the other one, it didn't feel straightforward, but like, yeah, it's actually it makes more, it's simpler to find, honestly. Yeah, so we're gonna have 1 here and here, because like you can only add 1 element before you need to extend it. And here, instead of 2 times the current size, we're gonna have 1. Why 1? Because I mean, we're always gonna be incrementing by, we're always gonna be have at least that much. What am I saying? No, that's not it. That's the size of the current array. Okay, so I want to create an array that is the size of this, plus a constant, which is here. So that's the creation of array part, right? On the other side, we had 2 times 1. Here, the creation will take that many steps. And steps, obviously, that will vary based on what C is. And if C is a big constant, or not. Then plus here we're gonna have for moving everything, we're gonna have only one thing to move, so we add a 1. And now, so just copy, and then we need to add our actual object to the array, like the thing we wanted to add in the first place, so just add whatever. And so similarly to the other one, that element will never change, like it's just a 1 that's there. The copy will vary based on, in a similar fashion to the other one, based on this. And the creation part is the thing that's gonna be changing. That's gonna be changing like I mean, yeah, it's gonna be changing in a pretty interesting way. Phase 1. So now that we got an array of size 1 plus c, right? Because we increased by a constant, we're gonna have 1 plus c operations. It feels weird because on the other side, like we add concrete numbers. Here we don't know what c is. If it helps you, just pick a random value for c. Like what we care about is the order of the thing, but I'm gonna keep it general for now. We have 1 plus c steps to fill the entire array, just because that's the amount of space we have in the thing, and until then we don't have to worry about creating something new. But then when that's done, special, you're gonna have 1 plus c, again, that's just the size of the current array, plus c, that's the new increment. And now, so that's the first term, creating. Then you need to copy everything over, so that's just 1 plus c. And then yet again, that will be plus 1, because we just need to add something. So those of you who are really paying attention to this, and if you are, really thank you. I know I might not be making a lot of sense, but there's a pattern that might be already popping up. Okay. For this one, I'll be collating the terms, just because it makes that pattern even more obvious. So I have 1 plus c. I had 1 plus c here. That was the size of the current of the array, right? Now I have 1 plus c plus c. I don't want to write 1 plus c plus c. I'll just write 1 plus 2c. I'll just pause on that, like, oh, interesting. Okay. Then I come here. The size of the current array is 1 plus 2c. But I want to add a c to that, because new increment. I could leave it as this, or I could just write this as 1 plus 3c. Ooh, interesting. What is happening there? Oh, okay. For copying, we're just gonna be copying the exact amount of data that we already have in the array, and then plus 1. If you want to take your time to like guess what the pattern is, just pause the video right now. But the pattern, I'm just gonna be spoiling it, is gonna be this. And this one, if you found it, good job, is gonna be this. Reg. See this? We're gonna have 1 plus IC. Okay. And for the special, we're gonna have here 1 plus I plus 1c plus, well, just this term here, 1 plus IC plus 1. This now, same logic as before. Now we got the amount of steps for any given phase. How many steps does it take to do how many steps will be dedicated to regular, and how many steps will be dedicated for a special push. But I want the total of this, so I will just sum it. this is there's nothing really complex here, like no power rules or anything. So I'm just gonna like write down what I have here, which is 3IC something. Where is it? Yeah, okay. Which is 3IC plus C plus 4. If you go back to the first step and like confirm it for yourself, you'll see that like this works and this will work for any given step. But that is our operation. Yet again, we want to find a general form, not just for not just for one thing. And so we will try to sum for all possible values of I. Okay, which is really why we want to generalize like that. Yet again, we start at 0. And we yet again need a top. I'm just going to write the rest of the thing. 3I plus C plus 4. We yet again need a top. The top here, how do I find it? Well, luckily, in this case, the relationship is a bit more straightforward, right? Because we see that we have IC here, 1 plus IC. And as this thing grows, since n is going to be, since this here, the amount of regular pushes, is the same as the size of the array, we know that at some point, n will be equal to this, like to an equation of this form. N is equal to 1 plus xc. Okay? And I'm on purpose not putting n equal to this here because I don't want you to like, I is any arbitrary index, and x here in that demonstration is the index for which we get n as the size. Okay, you would get the same top the same value if you just decided to set it here, like n is equal to that. But to not confuse already confusing terms even more, I'll just create x here that will be its own thing. That's the index specifically for n. And so now we fall back to high school, and it's really just solve for x. So n minus 1 is equal to xc. And what is x? It's n minus 1 divided by c. Boom. And so that means that for any given x, we're gonna for any given constant. No, how do I say that? We see that the maximum value that the index will attain, assuming that n is some really, 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 really big value. Yeah, that no, it's not the max value, but that the index for that nth length array will be given by that equation here. And since we're trying to solve for that biggest possible, like that worst case, we're just going to be plugging that index here, since that's what i's variation with respect to. And I hope you can see why I didn't set that n equal to that here, because it would be weird to have like I equal to that here and then I be, yeah. Math. Okay. So n minus 1 divided by c. The logic is going to be the same as what we did earlier. Just use your laws of summations. Constant terms are really just a matter of like multiplying by that. So you're going to get plus n minus 1 plus n minus 1 divided by c times 4, I think. Yeah, that checks out. And yet again, here I'm really going through the trouble of like doing the exact thing just because I feel like finding the exact polynomial for that algorithm. But if you're just trying to find big O, please make yourself a favor and like just ignore those constant terms. Like the important term is that one, the one that's varying here. Okay, so If I didn't make a mistake on the rest, that's just gonna be this n plus n minus 1. Yes, and then here we're gonna have 3 and c are constants, so we can just pull them out. 3c, and we're gonna have 3n minus 1 divided by c, I is equal to 0 of I. And so we see that we go 0 plus 1 plus 2 plus boom, 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 all the way to n minus 1 divided by c, which will be an integer. Yeah, what does that look like? Yet again, just pattern recognition. If you don't know, well, you don't know, and now you will know. This is the same as this here, n plus 1 divided by 2. There's a really nifty proof for like that thing here that I'll do after, because like this video is already super long anyway, so like what a few minutes more, like what a minute more is. But yeah, since this here is equal to this, and yet again that n is different from that n, so I'll just change that to m instead. M is yet again the max term we reach here, so I'm going to be plugging n minus 1 here, n minus 1 there. 3c divided by okay, 2, and then I have n minus 1 over c. Why did I do that to myself? N minus 1 divided by c plus 2 plus c. It's plus 1, but when I put it on the same base, it's plus c. Yeah, all divided by c though, like this. And so now it's a matter of like multiplying stuff together. This is on that level. I'm just gonna cancel this and that. Why did I do that to myself? Why did I do that to myself? Okay. Did I make a mistake? And yeah. Okay, no, that I think that makes sense. Okay, so now I got n, that those two terms here divided by 2. So 3 to the 2 is its own thing. Now it's high school again, so I'm just expanding the parentheses. N squared. Honestly, you could already stop here, because just from what we're seeing here, the biggest we had here was n, the biggest we had here was n, the biggest we had here, well, it's gonna be n squared, so we already know it's gonna be order of n squared. But if you're curious and want to know what the exact value is, assuming I didn't fuck it up, it's gonna be n squared minus n plus nc minus n plus 1 minus c over c over c. Yeah, so if we simplify, we get 3 over 2 minus 2, okay, n squared minus 2n plus nc minus c over c, and then plus everything else. So plus 4n minus 4 divided by c plus n minus 1. Boom. So I won't be putting them on the same denominator, because just that was already long enough. But we see that the highest order term is that one, and technically it's like n2 over c, but yet again, scalars don't matter. Scalars don't matter. Oh, wait, okay. Scalars don't matter, so in the end, the entire O specifically would be this, if I didn't make a mistake. But since we only care about the highest order term, the same way as like no one, the specific height of the Eiffel Tower has some amount of like micrometers, nanometers, picometers in it. Picometers, whichever is the right one. But no one will care, and like no one will care beyond the meter most of the time, because that's just the most important unit. So we only care about the biggest term, the one that grows the fastest, n squared. Boom. And so that's it. That's n squared. That's the other one is n. So clearly, just always use the other one. It's gonna be simple. Time complexity wise, it's gonna be simpler. Another way you could have seen that like this one would probably be somewhat fucked up is how, see how both we were dealing with indices, right? And special here is always going to be the most time consuming operation. But the thing is, because of how the function works, when we find the index for our n, if you remember, the index for the other one, for the doubling version, was log 2n. Okay? But when we find the index for our nth phase, we're already in terms of linear. Whereas when we were in doubling, we were still in logarithm. Okay? Which is a smaller order than this here. So we need a lot more phases to get to n when we're doing it this way, versus doing it with the doubling, where we get to like big values really quickly. But the thing is, since the regular is not that important really in the long run, like it amounts to something. But the thing that really takes time is this here. The fact that we have a lot more of this thing here than in the other one is gonna make this really heavy. And now that we're done with this, the proof, well, one way to prove, like you can just 1 plus 2 plus 3 plus all the way to n. The proof for y, that is exactly n to the n plus 1 divided by 2. You can show it by induction, and I think that most people will show it by induction. But a pretty cool trick is essentially to go at it that way instead. So you see how like this here, I could just summarize this as S, right? And we're gonna call S the sum. So S is just the sum of this. Okay? For now, we haven't proven this, so you can ignore it. So I come here, I have 1 plus 2 plus 3 plus boom, all the way to n. Okay, well, that's 1s. S is right there. This is a summation, right? So addition, I could swap this here, I could swap this here, I could swap this here. It doesn't change a thing. So I can take this here and write it that way instead. n minus 1 plus n minus 2 plus all the way to 1. And for now, why we're doing it is not necessarily making sense. And honestly, it's the kind of stuff like, I'm not sure how you'd find that on your own if you don't know the proof already. I think I'm just not that good enough at proofs yet. But really, that's the idea. Okay? So that's another summation. And those two, we agree, are the same, right? So if I sum them together, this, interestingly, is n plus 1. This also is n plus 1. This also is n plus 1. And you guessed it, that last term here is also n plus 1. So I don't know how many times we summed it, but we have a lot of summations of n plus 1. But the thing is, we already know exactly how many times we summed it, since that summation itself is telling us that, yeah, like I'm going from 1, and I end at n, so I have exactly n terms in this. So I'm doing n, I'm multiplying n minus n plus 1 thing. That n plus 1, a better way to see it, that n plus 1 term is appearing exactly n times in this equation here. The thing is, right now, this here is just 2s. And s is like the summation yet again, that's this, right? That's just 2s. So if I want it to be what I wanted to show at the beginning, I need to divide both sides. So that's just algebra. And then boom, we get s is equal to n plus 1 n divided by 2. And like, I know this is relevant in like when you're doing some difficult, like you use a similar strategy when you need to like solve some difficult integrals and stuff. But yeah, that's it's a really satisfying proof to look at, but like annoying to think of like how bright you need to be like find this on your own, honestly. But yeah, that's pretty much it. So never again will I record a video without a script, because that was way too long for what that was. But hopefully that was helpful, even with my ramblings. And yeah, there you go.